Dr. Geraint Taff Morgan. He is a FRAS MRSC who works in Department of Physical Sciences at the Open University in UK. Uh, of course, he has very long CV and he has done incredible work both on the engineering side and the healthcare side. But one part which I have liked the most, especially that he was involved in the designing, building, validating, and applying the sample prep system for the mass spec instruments, including the Ptolemy and GAP on the Rosetta and Beagle 2 missions in 2014, and these resulted into some big historic findings, and it was published in Science. His translational work has also received a lot of attention. Also, he has been featured in Times Magazine, New Scientist. He has given talk in Royal Society meetings, and of course, he has really accomplished and got so many awards to his name. His research interest includes applications of comprehensive gas chromatography to a range of analytical challenges. He's also involved in development of analytical assays and instrumentation solutions for various industries and different customer challenges. He's also having strategic initiatives for the space technology transfer to various other sectors, especially the healthcare. Today, he's going to give you some flavor of how mass spectrometry based technologies and applications could be utilized for a variety of applications, including space mission to clinics to terrestrial challenges. So with that, let me welcome Professor Taff Morgan, if can he hear us.
Taff, yeah, I can. Thank you.
Great. We can now share the screen, and we are eagerly waiting to listen to your lecture.
As Professor mentioned, what I'll be trying to do today is give you a flavor of how people like myself who design instruments and apply instruments for developing new assays, and how we can work with people like Graham and other specialists who develop machine learning and artificial intelligence software, how we can develop, provide them with interesting data sets. So all my work that I do is very much in collaboration with the end user of the data, but also people like Professor Geraint who can basically data mine the information that we can collect. So my expertise is in how do you get good data, reproducible data that can then be applied to look for and answer some of the questions that I'll go through today. So my talk really is called Down to Earth. I've been lucky to be on 2 space missions so far, which I'll talk about. And the thing about space missions is it pushes the boundaries of science and technology. It makes you think again about how you might deliver projects. So you don't have the luxury of mains plug. You don't have the ability to go back and rebuild something if there's a problem. So a lot of effort goes into the design and into developing new technologies, which can also be applied back here on Earth. So the top level title is From Sniffing Comets, the Moon and Mars to Submarines, Whiskey and Cancer. And that's only a snapshot of what I'll be talking about today. But I should also mention that that beautiful picture on the screen is actually a picture taken by a camera on the Rosetta orbiter as we were on our way to the comet. Going to the comet took us 10 years, and we used the Earth and Mars as a slingshot to allow us to get out in the solar system. So this is a picture taken by a French camera called Osiris as it flew past the Earth. So as I mentioned, I'm an analytical chemist. I work at the Open University, which is based in Milton Keynes, which is a new town, and the university is about the same age as the town. It's basically just over 50 years old, but we are the largest university in the UK with 180,000 undergraduate students at any one time, which is about 5% of all UK students. And we have about 1 in 5 of all MBAs studied in the UK is through the Open University. We have a mission which is different to most other universities. We have a campus, but no students are on campus apart from postgraduates. So it is a distance learning university. So Everything is done through the internet these days. It used to be done through TV programs and phone calls, but now it's done through the internet. And we are open to people, places, methods, and ideas. You actually don't need any qualifications, even from school, to be able to allow to study with the OU, which makes us unique. And we, you know, I don't know if you know where Milton Keynes is, but we literally are halfway between London and Birmingham, and Oxford and Cambridge. So we're right in the centre of the majority of research in the UK. And I'm in the group. I'm in the School of Physical Sciences in this wonderful building, where we have very well stocked laboratories, and we are the UK's largest astronomy, planetary and space science research group. And we have about 100 people working in these areas, as well as straightforward physics. So the journey I want to take you on today is something that's taken me over 25 years. It covers 4 billion miles around our solar system. And I'll start with the Comet work and the Rosetta space mission. So comets, I don't know if you know, are some of the largest structures in our solar system. So here's a beautiful image from the Southern Observatory, and you can see a comet tail in the background, and it covers most of the night sky. Now, in reality, the thing that causes the nucleus of the comet is actually much, much smaller. And this is just to give you an idea of size. This is the comet that we landed on back in November of 2014. It's called Comet Churyumov-Gerasimenko, after the two Ukrainian astronomers who found it. And just to give you an idea of the size, we were kind of expecting it to be a potato shape to start with, but it ended up being more like a rubber duck. So you can see it has a kind of head and a body, and the body is about 4 kilometers long, which is about the same size as Heathrow airport runway. But as you say, if we were to overlay it over London, it would stretch from Big Ben to the Tower of London. So something that's actually relatively small, because it's mainly made up of ice and dust. When it heats up and it comes towards the sun, it then evaporates, and that's what you see in the previous picture, is the tails coming off, which is basically the comet. Well, I suppose you could call it sweating, but it's basically evaporating away into the surface. This is a picture taken by the camera on the lander. So the instrument that I worked on was on board the Philae lander, and again, you'll see a video in a minute going through how exciting it was that week of landing. And in the background, you can see the picture of the comet. Again, you can see around about in the middle of the comet, towards the left-hand side of the head, there is a jet coming out. So that's where the gas was coming out, as I said before. And this is probably the world's most expensive selfie at just under €1 billion. And it's beautiful because it has one of the youngest things in our solar system, which of course is the solar panels from the orbiter, and one of the oldest things in our solar system. So comets are left over from the birth of the solar system. They occupy a space well beyond Pluto, called the Kuiper belt, or these comets are believed to be left over from the beginning of our solar system. So there's something like 4.6 billion years old. And so the interest in going to a comet is to try and work out, did the building blocks of life on Earth, were they seeded from a cometary impact in the past? Does the comet contain such materials? And the other thing we were trying to look for was, does the water on a comet, is it consistent with the water we have on Earth? I don't know if you know, but water can be measured through looking at its isotopic composition. So the isotopic composition of anything will be dependent on its formation process, and therefore you can, using isotopes, so looking at the hydrogen isotopes and at the oxygen isotopes, you can in theory fingerprint where something's come from. So one of the theories is that early on in the Earth's history we were hit by a comet, and that's what brought the majority of the water to the Earth. Because there's a lot more water on the Earth than should be here based on just pure geology. So I'm about to play the video now, so hopefully you'll be able to hear the sound as well. If not, if you can just put it up in the chat box, then I'll then give an audible commentary.
First ever landing on a comet was filled with.
We can hear, yeah. Did it become mute again? It was started. So now we cannot hear audio.
Okay, so this is the project manager. So these are all the dignitaries from all the different space agencies, obviously celebrating. So this is the this is actually what we now know happened to the actual lander. It actually bounced across the surface of the actual comet. So we bounced across the head, and so in a minute you will see an image showing where we actually landed, and we actually landed within a football field distance of the original plan, which is quite amazing when you think that the actual comet itself was tumbling in multiple directions. And this is just showing you the track of the camera. So this is filmed from the orbiter, and we ended up actually landing underneath. This is a picture taken by the camera. Again, this is just showing you where we landed initially on the left side of the little square, where we finally landed in the diamond. So we bounced across that crater. Luckily for us, we did actually land on this. Got captured by the comet. So this is just showing the dust and eventually where the Philae lander actually finished. The lander itself is the same size as a washing machine. It weighs just over 80 kilograms. And this is then a picture of our landing site. And on the left-hand side, the thing you see is actually the feet. Again, there are two more of the feet you can see, and then the image is taken. So there are 10 instruments on board. Philae, which is the instrument I worked on, was one of them. But we had cameras. We had was looking at things like the strength of the surface. We also had another mass system called COSAC. With the SD tube to drill, and that the idea was it would drill into the surface and get samples for us. So after 10 years and 4 billion miles chasing the comet around the system, we did finally land in November 2014. And the data, this footage was released a week after landing, so very, very quickly. And so this guy is of the name. So this is the man who discovered the comet, meeting all the science and engineering team from Beta. And what he said was, this now is just talking about organic molecules, and it was our experiment. Basic information about the presence of organic molecules. So the building blocks of life are on the surface of a comet. Unfortunately, we didn't actually get an ice core sample, so we didn't get to analyze the water to try and do the measurements. But our colleagues on the orbiter craft did, and they were able to determine that actually the isotopic composition of this particular comet is different to that of the water on Earth. However, there are 1 trillion comets, so it could be that one of those brought the water to Earth. So this is the data we got back. It's my colleague Andy Morse looking over his shoulder, and on his screen you can see the actual data that's come back from the lander. It took about 35 minutes, I believe, to go from the orbit to go from the lander to the orbiter to Australia to Germany and then to France, and then we were sitting in the lander control center in in Germany, in Cologne, and Andy there was able to log in and get the data off the French portal. The picture on the second picture of the guy with the beard is our German friend and colleague, Fred Gersman, and he had the Kozak instrument, and he had the longest 20 minutes of his life waiting for his data to come through, because his experiment ran directly after ours. So we sniffed the atmosphere after we hit the comet's surface, and we were able to analyze the dust and the gases that came in through that. Luckily for us, or luckily for all of us really, Fred also did get data, and it looked pretty much the same as what the data we have shown on the screen there. So it's mainly water, carbon monoxide, carbon dioxide. But as I say, poor old Fred had the longest 20-minute wait of his ever lifetime. And the data you can see as we've got there, the sniff one. So basically we had collected data about 8 minutes after the first touchdown. So as we were bouncing across the surface, we were able to take the data. And the nice thing is that in the previous sequence you saw in the video, there was a photograph taken of the lander. At that point, we took that data. So this is the instrument we built. It's a miniature gas chromatograph isotope ratio mass spectrometer. So basically, the gas chromatograph allows us to separate the different complex molecules, a mixture of molecules, and an ion trap mass spectrometer, which I'll show you in the next slide, allows us to analyze its chemical composition. So this is the same size as a shoebox. We shrunk the laboratory instruments, which are the size of a family car, down to something the size of a shoebox. It weighed just over 4.5 kilograms. It used less power than a light bulb. And yet, after 10 years of in fact, nearly 14 years of not touching it, and it's surviving the harsh environments of space, going down to something like -40, plus 70 degrees. It switched on and it worked. And on the top right, you can see the paper we had from Science, where we were able to say that the dust particles on a comet do contain complex hydrocarbons, mainly with the carbon, hydrogen, oxygen kind of repeating chain, which from the scientific perspective is what you might expect, because you get photochemistry of species like carbon monoxide, carbon dioxide, methane, and water would give you these kind of long chain molecules. Probably of more interest really was the data we got in the bottom left, which was the data we got after we'd landed and were stuck under the hull. And we were able to measure the carbon monoxide to carbon dioxide ratio and compare it to the values that the orbiter got. And our values were completely different. The ratio was something like 15 times different. And one of the potential reasons for that is that the funny shape of the comet, where you have a ball and then a bigger body, might have been caused by the fact that you have actually two comets that have collided early on in its history. And that would explain why we get a completely different number. We're measuring a point source on the head, whereas the orbiter is measuring an average value for both the lobes of the comet. And what you might expect is that when the comets were formed, the ratio of carbon monoxide to carbon dioxide is actually determined by the radiation environment at the time. So if the comets formed in different places, they would have different ratios of carbon monoxide and carbon dioxide, because photochemistry would result in the carbon dioxide breaking down into carbon monoxide. The picture at the bottom right is just showing us from the very first thing that went on to the Philae lander. So there we are in September of 2001, delivered and ready to go. And as I say, it wasn't until November 2014 that we actually got the data back. And here's the miniature mass spectrometer we built. So it's an ion trap mass spectrometer, which is good for working at relatively high pressures. We designed this ourselves. We took all the mass out of it. You can see the actual mass of the electrodes of the mass spectrometer are less than 50 grams. The power was very, very low as well. And we achieved that by removing the traditional filament that's used to ionize species, and we replaced it with the so-called field emission or nanotips, which are little silicon wafers that have very, very sharp points, and they can release the electrons, which allow us to then do the ionization and then do the detection in the mass spectrometer, but with significantly lower power than having to heat a filament to well over 1,000 degrees. The mass of the whole thing, I said, was 4.5 kilos. But again, you can see that the mass spectrometer itself weighed less than 500 grams, including all the electronics and HV, which is in the box underneath the mass spec on the left, and it was a cube of about 10 by 10 centimeters. One of the big problems we had, of course, you saw in the video, was that we only had about 2-3 days of data from the lander because it had fallen underneath the cliff. And despite the best attempts of trying to make contact with the lander again, we failed. We got a signal to say that it had woken up and the batteries had recharged. You can see the outside of the actual lander has solar panels. Unfortunately, because of the angle of the cliff we were stuck underneath, we weren't able to get lock on for the data transmission, and so we never actually got any more information back from the lander after those first few days. But just before the end of the mission in September 2016, we did actually get data back, or rather, images were taken by Osiris, which is the same camera that took the picture of the Earth for the very first slide, and they were able to find the lander quite clearly, as you can see here, trapped under the cliff. But that was just literally 3-4 weeks before the orbiter was landed into the actual the comet. So for those of us on the lander, it was nice to be able to have closure and understand what had happened to it, and clarify that all the hypotheses about what had happened to the lander were actually true. And it's just amazing we actually got data back at all, which is fabulous. The other mission I've been involved with was actually to go to the Mars to look for signatures of past and present life. Past life would have been done by doing experiments we normally do with meteorites in the laboratory, which means you burn the meteorite in stepwise fashion, and you're looking at the release profile of the different types of carbon present, and you're also looking at the isotopic composition. So this instrument was slightly bigger. It was about 6.5 kilograms, and fitted into something, the Beagle lander, which was developed by Colin Pillinger, who's the man in the middle of the picture, the photograph. I'm to his right hand, to his left, in the black t-shirt. And this, I can tell you that this picture was taken in 2003, sometime before June and December. And I know that because the guy to Colin's right, in the jumper with a white collar, is Professor Ian Wright, and he normally has very long hair. The one time he cut his hair was just after Beagle 2 launch, so given he's got short hair, that means we can recognize when it was. Unfortunately, the Beagle 2 mass spectrometer, the Beagle 2 mass spectrometer was designed, was a magnetic sector mass spectrometer, and it was designed to look at isotopes. Unfortunately, Beagle 2 was due to send a signal back from the surface on Christmas Day of 2003, having launched in June 2003 as well. And unfortunately, we got no signal back. There was a big inquiry about what had happened, and was it what had failed. But in 2015, NASA were imaging with a high-rise spectrometer. We're looking in the region where Beagle should have landed, and they found this very light colored bright object in the right place, about the right size, and they've concluded that what's happened is that the Beagle 2 lander has landed successfully. It has opened up, and unfortunately what's happened is the last solar panel, or the last 2 solar panels, failed to deploy, and unfortunately our radio transmitter was underneath the last of the solar panels. So we now believe that Beagle 2 landed safely, so the entry, descent and landing all went well. It's just for some reason the last 2 solar panels didn't deploy. It could have been trapped under an airbag, or it could have been trapped under a rock, next to a rock, and therefore it didn't open. But anyway, again, for those of us who worked on that project, it's quite nice to know that actually we got a lot closer than we thought. you know, things could have been different. But that's the risk of space missions, unfortunately. Even the Americans only have a 50% record of landing on Mars. The Russians have, like us, a 0 success rate. Europe's about to go back there, hopefully, in the next few years. So hopefully we'll get even more fantastic science. The other place that we're involved with is going to the moon. You probably saw all the news stories recently about water on the moon. And that's really quite a big story. So we are involved in a Russian mission. We are the European suppliers of technology to try and look for volatiles in the south pole of the moon. Why is that important? Well, because it becomes so-called in situ resource utilization. So if you have water on the moon that you can extract, that you can process, then you have the source of, obviously, water. You also have a source of hydrogen. You have a source of oxygen. So that would allow you to have then potentially people like Bezos, who own Amazon, want to then go and look at potentially using the moon as a kind of off-Earth manufacturing facility. Or if you're Elon Musk, you want to use the moon as a petrol station on the way to the rest of the solar system. So you could imagine that you could actually produce quarters for people to live on the moon, to extract resources, and then instead of launching from Earth, you would launch to the moon, and then you'd launch from the moon to the other sources, which has a much lower gravitational field. And of course, you'd be able to use the resources, hydrogen, oxygen, as the rocket fuel. So we have a couple of projects, one with NASA called which is going in the next, hopefully in the next 2 years or so. But the longer one is to develop a system reusing the 2 instruments we've just been talking about, but using them on the moon to look for water and also to look at other volatiles present as well, with a view to it being used as basically future resources. So you may be wondering, what has space done for the Earth? Well, actually, it's really quite amazing. I didn't realize this until I went to Australia a few years ago, that Wi-Fi that we all use in our phones and mobile laptops was actually developed by some radio astronomers in Australia, working at the CSIRO. They developed some technology to stop basically interferences in their signals, and suddenly patented the idea, and it's now been, even by just 2013, it's been used in over 5 billion devices worldwide, and has made the CSIRO a lot of revenue, which is great, and because it's being fed back into the Australian Science Network. Given that Wi-Fi is so prevalent these days, I will never be able to develop anything that's going to match that. But for the last 10, 12 years or so, I've been trying to translate technology. And the next video will hopefully show you other technologies that have been developed and translated from space. Now, this normally comes with music, but I'll just let it play. It only runs for about 2 minutes anyway. But hopefully you'll see some interesting technologies.
Audio is working this time.
Sorry?
Audio is working. Yeah, please go ahead. Is there anything which is to be watched in the commentary as well, or because audio now got mute?
Sorry?
There is no audio now in the video.
can see there's plenty of technologies coming out of space translation, and there are now, I believe, 70 different ESA-BIC communities around Europe who are all trying to help in translating space technology. So the rest of my talk really is about how we translate this know-how to terrestrial samples. So two of the actual applications there were mine. So one is the bedbug detection, which I'll talk about a bit later, and the other one is the safer submarines, which again I'll talk about. But the problem with space missions is they tend to be a bit like London buses. So you hang around for ages and then three come at once. So we had Rosetta, Beagle, and Cassini-Huygens, the mission to Titan, all at the same time around about 2000. So 5 years either side of the millennium, basically. And it's only fairly recently that we've had any more missions, mainly because, of course, the projects or potential space missions cover a very wide range of application areas. And it just so happens that our potential technologies have not been of value to the most recent missions. But anyway, we've been looking at how we can translate our expertise, working in collaboration with end users, both academic and more recently commercial, to try and find how we can exploit our expertise and deliver solutions to challenges back here on Earth, including healthcare. So one of the technologies that has come out of the Philae instrument is this valve. So I'm a co-inventor on the patents for the valve, and it's a very, very small valve, but it can go, it's very, very leak tight, but it's also can have survive very high pressures. It has no rubbers or plastics in the wetted parts, so it's quite good for materials that, well, it's good for situations where rubbers and plastics would not be good. So in particular, space missions where you have very high and low temperatures and you want to keep the gas for a very long time, but also we're looking at things like translation to the hydrogen fuel sector. So the hydrogen economy is becoming really big in the UK and in Europe, replacing of hydrocarbon fuels by basically water and using electrolysis to produce hydrogen and oxygen. But you need to then store those gases, and that's where our valve comes in, because it can store them without losing it, but it can also be proportional valve to allow us to meter out those high pressures into the different scenarios. So we're in conversation with a number of different people, including people who are developing trains and buses and even cars using hydrogen. So it's a very exciting time for us, and hopefully our valve will become an enabling technology in that sector. In terms of what's the biggest impact we've had so far, well, we have developed the air monitoring system that will be used on all future UK submarines. So it measures, the submarine is basically a big metal tube, the size of a football pitch, and it has 100 people on board. In the case of our strategic nuclear defense capability, that submarine is stealth and goes under the water for up to 3 months, and no one can know where it is. To do that, you obviously need to be able to generate your own air and measure the quality of that air, and that's what our system does. So this is breaking a 30-year American monopoly on the provision of these types of systems to the NATO fleet. And we have now translated this technology following a very successful sea trial to a UK company that has taken it forward from where we took it to TRL 7. It's now fully at TRL 9. It's actually installed on a submarine, and the submarine will go to sea next year. But as you can see from the bottom there, the advantages of the system are it's faster, it's better, and it's cheaper. So, and as importantly, it's a UK capability now. And so if there are any problems with the systems, it can be repaired in a timely fashion. We also work with the world's largest fragrance company. So we've developed 2 systems for them, one of which is being used to replace microplastics in domestic products. So Givaudan supply about 1/4 of all the world's flavors and fragrances, to all the big companies like Unilever, Procter & Gamble, Johnson & Johnson, all the people who make shampoos and washing powders and toothpaste and all the kind of stuff that we all use every day. So we're helping them develop, being able to evaluate their new formulations. We've also developed a separate system which allows them to evaluate their new products. And the system we've built is a fraction of the size, a fraction of the cost, and allows them to use 1 milligram of any new compound rather than one gram. So it's 1,000 times less material. And the sample throughput is something like 50 times faster. So again, we're providing tools that enable people to deliver their products more effectively and more efficiently. This is my lab area. So you can see we're full of lots of machines, mostly GCMSs, but we also have other detectors as well. Each machine kind of has its unique USP, so we can use it for doing different things. But we can handle samples that are gases, liquids, or solids. And we can have gases sent from all around the world to be analysed. Here are some more of the instruments, and these are the more expensive ones because these do something called comprehensive gas chromatography, which basically is 2 GC columns separated by a modulator. But what this allows you to do is separate the small compounds away from the really big ones. So potentially giving you the answer to the problem, because Murphy's law would say it's going to be the small peaks that are hidden that are causing the problems, or are the indicators perhaps of a health condition, or what have you. So we have some of the best equipment in the world. We work very closely with the companies to develop solutions, as I say, for a whole range of customers. Just an example of some of the trade publications we've done. So the one on the left is whiskey. The other two in the middle are pesticides, but working with a gas generator company. And there we were evaluating the use of hydrogen rather than helium in the mass spectrometer, and concluded that hydrogen is not as good, but for the vast majority of people, it's still perfectly fine. So again, it's about being able to demonstrate the impact of changing parameters. On the right-hand side is an article in which we did the first fully automated analysis of cannabis metabolites present in hair samples. So again, the idea that if you can take the human out of the process, you can be more efficient. You can actually run samples 24 hours a day. So this is all about using robots to allow us to improve our efficiency. These are the people who actually do all the work. So these are Simona, Sonia, and Rachel. They're all three, you can see, PhD postdocs, and they all work in the lab running all the different systems for me. I have to admit that I've been at the lab so long now, I don't know how to run the machines. We have a range of programs where we get funding from. So this is a so-called Sprint program. So Sprint is all about technology translation, and there's 5 universities involved. We had 4.8 million between the 5 universities over the last 3 years to engage with SMEs to then develop solutions in a whole range of different application areas. And these are just the projects that I got funded. So starting with Scotch Whisky, which I'll talk about in a minute. The most recent one is a project with H.E. Stringer, and they're a flavor company who are very keen on looking at how you might replace meat flavors from products, but using plant-based materials. So apparently they can give you the taste of bacon without the pig by using plant materials. I've had 2 projects funded with Efficiency Technologies. One has developed a new type of brandy for the market, which is currently being reviewed by 2 supermarkets, and we help them in their characterizing and optimizing their industrial process by which they could do that. The more recent project that's just started is looking at how we can help craft beer people and also artisan distillers, people who make gin and whiskey and whatever, how we can help them develop new tools to allow them to help the craft beer people optimize their measurements and their processing. TISIX is our largest project. It's looking at TISIX produce gas tanks, very light gas tanks, but using composites. And we're going to be sniffing their samples to allow them to basically be more efficient and be able to produce their systems more quickly, because they use glues to outgas, and we can help them in that measurement. Nutripharma is a company who are basically developing food supplements, but using food waste, or rather using the bits that the supermarkets don't want, of things like celery and other brassicas and whatever. So we're helping them characterize the nutrients that are currently going to landfill, and how it might be they can put those into protein shakes and other kind of produce. LACO is the American manufacturer, and we work with them to a whole range of different projects, looking to try and help them characterize the best use of their system, with a view to them then selling their £250,000 machines to around the world. And I'm aware that actually there's a LACO system in IITB. The last one is AVS, and that's a satellite company, and we're using the valve. It's been evaluated by them currently for use in a new propulsion system that they're developing for satellites, which uses water rather than hydrazine. So again, it's electrolysis on board a satellite, which then generates hydrogen oxygen, which we then help store, and then it goes back to an engine, which then converts it back to water, and it's the water that's squirted out of the satellite. So that is much safer, but it's also, or rather much more environmentally friendly rather than hydrazine, but it's also much safer. And so it will save them £500,000 per satellite in safety features on the ground, because water is not an issue, but hydrazine release is. Just to show you all the projects we have, and Martine on the left, on the right hand side there, she's our coordinator at the OU. Ross, who's got the big smiley face, he was at the OU, but is now the director of the Sprint program. And then Professor Andrew Holland and myself are involved at the OU in terms of we're looking for follow-on funding for the Sprint program. But as you can see, in the last 2 years, we've had over £800,000 worth of projects funded through the Sprint program to work with SMEs. In terms of Scotch Whisky, we're working with Scotch Whisky Research Institute, who are the trade body for the Scotch whisky industry, but also IBM Research to develop automated assays, but also machine learning algorithms to detect fake and adulterated Scotch whisky. Why is that important? Well, Scotch whisky sector is one of the biggest producers of spirit in Europe, which is in itself is worth 5 billion. It's worth over £1 billion in taxes to the UK economy. We have 128 distilleries employing 10,000 people and 40,000 jobs across the UK, with 7,000 of those being in kind of the rural areas of Scotland. So it's very important for those kind of communities that we continue to protect the brand. And you can see we're exporting to a whole 180 different countries around the world, including India and China, which are growing as markets. Just a quick show you using the GCGC, just to show you, you can see just straight from the picture that the compounds present in Macallan are completely different to those that are present in Islay. So Islay are basically peaty whiskies. So they use a peat fire to smoke the barley when they dry it, and that adds flavour. And you can see different compounds being present compared to what we have in a standard kind of whiskey. So as I say, we've been developing these algorithms, and they seem to work quite well. We can also do things like batch-to-batch discrimination, which would help again, if you're a maker of an expensive whiskey, you want to try and make that whiskey the same every time you make it, this year, next year, and even within years. So we can provide them with the kind of analysis tools which might help them improve that presentation. We were due to be presenting this to the World Distilled Spirits Conference in May. Unfortunately, COVID's got in the way, and that's now been delayed until September of next year. However, IBM have already tweeted and had a blog about this. We appear in the SWI annual report as being a new technology, and we also appear in the OU London Economics Impact document, which says that the OU itself, not just my project, but the OU itself has a just under 3 billion impact on the UK economy based on its activities. We also work in food, so I'm a member of the STFC Food Network. Again, this is a program to translate space-like technologies to the food sector. So we've developed processes to look at and identify the markers for fungal infection in avocados, looking at the shelf life of bagged salads, and more recently looking at chickens and the presence of the primary cause of food poisoning. And we have a current project looking at listeria on salad leaves as well, with a group in Cardiff. We can use this technology as well to look at complex mixtures. So this is looking at some illicit drugs, and again, you can take blood samples and take urine samples, and you can extract the drugs that are present. And this is from my former PhD student, Bill Guthrie, using the GCGC systems to separate all the different types of drugs that might be found on someone. And that's more recently been taken forward. We're funded by the American sports anti-doping charity called the Partnership for Clean Competition, and Rachel's our postdoc working with myself and Nick Turner and Tom Bassendale to develop a new screening methodology which will hopefully pick up the drug sheets. And why is that important? Well, because 7 of the 8 fastest men in the world have all been banned. Only Usain Bolt is clean. But again, just showing you how we can separate very, very similar compounds using this GCGC technology at levels that are appropriate for the World Anti-Doping Agency. So less than 2 nanograms per milliliter of urine of each compound. What I should also say is we're not just looking at steroids, we're also looking at the metabolites as well, because of course these compounds will break down quite quickly. So one of the ways of catching people is not to look for the drug, but to look for how the body processes the drug. And so we have now got some samples from King's College, which we were the people who did the drugs testing for the London Olympics in 2012. And there are over 70 compounds we need to be able to separate and identify. We've also looked at TB. This is an old project from 2008. We developed a mass spectrometer system. You can see in the picture there. The idea being that is a small system that can go out into the real world. And then again, we were looking at using GCMS and looking at specific markers that are present in the cell wall of TB. So these are so-called thiocerol dimycoserosates. But again, these are unique to a very low number of mycobacteria. And just to show you, this is what a positive sample at the top looks like and what a negative sample looks like. So because of the chemistry, we know what the ions of interest we are looking for. So in this case, we're looking for mass 101 and mass 88. So we're amongst all the kind of ions that would be present from 50 mass units up to 450, we can fingerprint and target and look at those specific ions to allow us to get low levels of detection. In terms of that technology, for humans, it kind of got taken over by something called Cepheid, which is a PCR technique. But we're now got funding more recently to try and apply this to look at the cattle version of TB, which is called bovine TB, which is a kind of sister mycobacteria to what we have. And in the UK, we have a real problem with TB in cows, which means that the cows have to be slaughtered. But it's believed that the transfer mechanism is because of badgers, which are a native species. And so we're in the process, hopefully, of developing a technology that could allow them to evaluate if badgers are actually positive or negative for TB. Unfortunately, this project has been heavily hit by COVID, and so we hope to restart this work in the next year, next 2021, because our colleagues haven't been able to collect the samples. In terms of medical diagnosis, we had a project, my PhD student here, Diane Turner, looked at samples that were originally looked at by dogs. So dogs have been shown to be able to sniff cancer. So the urine samples that were used for that, we have also had from colleagues at Amersham Hospital. There's 120,000 men in the UK have a positive PSA test. Unfortunately, 2/3 of those men will actually have a false positive diagnosis, which means they go through invasive tests, usually through the back passage, which A, is not very nice, and B, will result in transfer because it uses needles that fire through the back passage and into the prostate, will result in infection. And in theory, we can stop many of those tests by having a different diagnostic. So again, we were using the idea here was that when you go to see the GP, you can provide a urine sample. The urine sample will be analysed, and when you go to see in the hospital, you go and see the consultant, they will already have this data, which will help them piece together the different kinds of information, so they can actually use it in the patient pathway and make true decisions. So we had a limited number of samples, but we had, as you can see, we had about 40 samples for each of the different cases. So the problem with prostate cancer is that as a men, our prostates will grow, and therefore the symptoms you get, which is going to the toilet more often, or being unable to empty your bladder properly, or having pain in the region, it can be indicative of just having benign prostate hypertrophy, which is just a swelling of the prostate, which isn't cancer. And that's what the PSA is getting wrong. It's picking up the markers of the BPH and not of cancer. So we then analysed these samples. Diane, during a PhD, developed a throughput method, which is very robust. But basically, we need less than half a milliliter of urine, so 1/10 of a teaspoon, to be able to analyse. And then we originally worked with a guy called Michael Cauchi, who was using machine learning. The problem we had was, at the time, his computing power and the tools that he had couldn't use all the data. So the data you get from a mass spec is on one axis you have time, but you also have the different mass units, as I say, from 50 to 400 or 500 mass units. And each of those mass units will have an intensity, which will change over time, depending on what compounds are present. Unfortunately, in Michael's case, he had to collapse the MZ value, and what we end up with is something called a total ion chromatogram. So this is kind of an overview of what's actually happened. Even so, Michael got decent results, so we were around about between 75 and 80% accurate. But more recently, we've been working with Graham, and Graham has been able to look at all the data. And as you can see, using the same data sets, we get incredible sensitivity and specificity. And the graph at the bottom, but the only caveat is that that does contain some technical replicates, which from a modeling perspective means that we could, in theory, be having models in the training and the evaluation set. So Graham did a smaller study where he just took 20 positives and 27 negatives and looked at the sensitivity. And even so, the sensitivity and specificity is still remaining quite high, despite, of course, having very much fewer samples and therefore any negative, any wrong result having a bigger impact. But just to quickly, the graph at the bottom, all those things you can see, the names on the axis are basically the patient samples. They're all the negatives are blue and run effectively along the axis until you get to the red ones, which are the positive cancer samples. But you can see we have got some BPH and some blue controls in the positive samples, which is why we haven't got fantastic, well, we haven't got complete sensitivity. But the reality is it could be that those patients were really true positives, but weren't being picked up by the existing techniques. So what this data shows us is that we have a good tool, but that tool needs more investigation. And so we are looking for clinical partners to take that work forward. I'm conscious of time, so these are some of the companies I had. So one of my companies is basically sniffing bed bugs, or is developing technology to be able to sniff bed bugs in hotels. And that's because things like bed bugs actually communicate not by sound, but by chemical signatures. So those, once you know what those markers are, you can then try and detect them at really low levels and find them in systems. Of more relevance to this, really, at this stage, is the work I'm doing in Oxford Micromedical, which is another of my companies, and we are developing a test called the Urea breath test, which detects the presence of Helicobacter pylori. So in places like India, potentially up to 80% of the people will be infected with this bacteria. It's a bacteria that gets underneath the lining of your stomach, the mucus lining in your stomach, and allows the acid to attack the actual cell, the lining of the stomach, and therefore potentially causes ulcers. And in 3% of those people will go on to develop cancer. I believe stomach cancer is the second biggest killer of people in India. So potentially this is a breath test that allows you to detect the presence of the bacteria. And the reason for that is if you give people a tablet containing labeled urea. If you don't have the bacteria present, your body does not have the enzymes that will break down the urea. If you do have the bacteria present, then the urea will be broken down and converted to carbon dioxide. The carbon dioxide comes out in your breath. The labeled carbon dioxide will then change. So if you take a breath sample before and after the tablet, you'll be able to identify the presence of this bacteria. So this system is already used widely. You can see from even back 20, 30 years ago. But what hasn't been available before is an affordable and transportable detection system. So we're taking the technology that we use for looking for life on Mars to try and take it forward and make it affordable to actually be used in the developing world, and use it in places like India potentially, where we can actually take the instrument to where it needs to be to allow people to have access to this result. So we're working in collaboration where we have secured investments to allow this to happen. Unfortunately, the money still hasn't transferred yet. I'll be probably getting very old by the time it does, but we are assured it is going to happen. We're working with people like Tech Mahindra to turn this point-of-care device into an internet-connected device, although that's obviously gone quiet as we're waiting for the funding. I have a PhD student from Delhi who'd worked in the area of healthcare, and I collaborate with two colleagues who also have experience of the med tech industry in India, and also the Indian public health system. So that's a technology we hope once we get funding. Where are we going in the future? Well, potentially you can micro machine gas chromatographs to make them really, really small. So you look at something there that's the size of your thumbnail, and being able to separate compounds of interest. It's still a work in progress. The hardest thing actually is to join things to it. But in theory, if we can do the assays to look for the markers, and we know the markers can be separated, then you can design systems that can be really small and can be handheld. So this is where we're trying to go to going forward. And just to summarize, we have a track record of delivering sector disruptive solutions based on our heritage of space missions. We have some of the best analytical kit in the world, and we're looking for partners. So we need to work with the end users. We need to work with the instrument manufacturers. We need to work with doctors, engineers, whoever. But ultimately, we're always trying to develop a solution that can be delivered, and ultimately with impact, so that it gets to as many beneficiaries as possible, and it answers the question, so what? So how do we help people live better lives? Thank you. Hello?
Dr. Morgan, it was really wonderful. So truly eye-opening, starting from a space mission to looking at even the wine, and looking at bugs, and then looking at the PSA kind of medical test, all tuberculosis, all of them are really, really complex problems. You have really made tremendous contribution to a variety of sectors. So thank you so much for delivering this wonderful lecture. Any participant, any questions? Being a Saturday evening, I think some people have left. Professor Morgan, I have one question for you. So let's say when you're looking at these samples, these are probably for the tuberculosis I'm asking. So these are urine sample. So you are looking at urine metabolites using GCMS. And
no, sorry. In the TB work, that is actually from sputum.
Okay, sputum, right.
So those were pellets extracted from sputum. In the badger work, we are looking at urine, yes. So again, it would be very interesting, as you say, to then, if we can do it in urine,
right?
Could we also do that in humans? So that would be a really interesting question, yeah.
And also how so based on these metabolites which you are identifying from GCMS, what is the panel size which is able to distinguish so well? I think what you showed Graham's work. What was the number of metabolites over there?
A good question. That's a question for Graham, really. It was surprisingly low. It was probably 4 or 5 ions that were given the majority of the signal. So so yeah, it's an interesting one, because again, and I think that's where my approach differs to the pure biochemical people, or who are coming from it from a, they have target compounds they're looking for, whereas I take the approach like dogs. I think there's a signal there. I don't know what the signal is, but working with omics people, can we then work out? And again, that's the next step, I think, in terms of going beyond with Graham, is to say, okay, how does that then, once we know we can detect a difference, what is causing the difference, and how do we then translate that back to the work that you guys do, which is, you know, how do we then translate the volatile omics back to biology and understand the proteomics, and also then, you know, genomics as well, as we discussed at BDPM, you know.
Right.
We're kind of coming at the problem from two different directions, and